Okay, now don't forget all of this Maxwell stuff. It looked promising. It looked like a really good solution to a lot of problems. But this is science, right? Math is great. Math usually is what leads us to our next big discoveries, but we have to actually go make the discoveries. We actually have to go get experimental evidence for what the math might predict. And so Hertz did that. Okay, so Hertz went ahead. Hertz, you might recognize him from the unit we use. Yep, same Hertz, okay, the unit for frequency. So and it actually, a lot of it comes from this experiment. That's kind of why he got the unit named after him. So what did he do? Well, he basically set up a funny looking conductor that we now call an antenna loop. Okay, so an antenna. It basically, he set this up, okay, nearby to this fancy setup. What's the point of this fancy setup? All it really does, all the whole point of it is to change the electric field. Okay, so all this really acts to do is a changing, right? That's really what this does. Essentially, this produces a high voltage back and forth so that you get a buildup of charge here, and then it jumps across, and the charge here jumps across, jumps across, jumps across. So the direction of the electric field is basically being switched back and forth and back and forth. You have an accelerating charge, right? Okay. Now, so I should say a change electric field because of the accelerating charge. Okay. Now, what do we know? An accelerating charge produces what? Well, it produces electromagnetic radiation, right? It produces a changing electric field, which produces a changing magnetic field. Okay, and so if Maxwell is correct and any accelerating charge produces some wave that's going to go out and propagate and travel some distance, right? Then eventually those waves should hit this antenna here, which is a conductor, right? So if a changing electric magnetic field arrives at it, well, then it should maybe induce a current here, right? And sure enough, it did, right? And it kept hitting and kept hitting and kept hitting and kept hitting. And so what you were getting over here was a spark, right? You were getting a spark like the spark produced here, sitting across, no connection, nothing like that. You were getting a spark back and forth, right? And it sparked, wouldn't you know it, it sparked with the same frequency as the transmitter. Okay, so we call this the transmitter and this the receiver. It's receiving it, but it's really just called the antenna. Okay, and the antenna sparked with the exact same frequency. Why? Again, because we had an changing electric field, so that would do this, right? Why can it do that? Because it wouldn't normally just do that, but it can do that because when an electric field changes, well, the magnetic field changes perpendicular, right? And so we get an electromagnetic wave. Okay, so an electromagnetic wave. Okay, so I know I've shown you kind of a stationary picture of it, right? But what does an electromagnetic wave actually look like? So this is kind of what it looks like, right? You have a changing electric field. Notice the red is at this one point in space, right? The red arrow shows you what's happening with the electric field. The blue arrow shows you what's happening with the magnetic field. Magnetic field is kind of going, it's flat along that floor kind of axis there, right? Whereas the red one is coming up and down along this Z axis, right? This Z axis here, the wall kind of axis. And they're both propagating along this they haven't labeled it, but this would be the y-axis, right? So they're moving the y-axis. The red one is changing in the z-axis, and the blue one, the magnetic field, is changing in the x-axis. They keep propagating because a change in E causes a change in B, causes a change in E, right? So that is what it looks like. Okay, just another kind of view, a side-by-side of a mechanical wave versus a light wave, right, or an electromagnetic wave. You can see on the E axis for electric field as it changes like that, right? At each point, that's an electric field vector, okay? And then at the B axis for magnetic field, you can see it's just doing that in the other one. Which way do they go? This way, all perpendicular to each other. Okay, so back to Hertz. So what's happening? This thing's happening, right? We have here, okay, we have a discharging spark. So you can see these black lines here, these are the electric field. It's changing, it's swapping. So you have a charge accelerating, right? An electric field kind of changing around it because it's accelerating. Hey, changing electric field, that's going to propagate through space as long as there's a changing magnetic field to also help it keep propagating, right? Which of course, that's how an electromagnetic field works, okay? An electromagnetic wave works. And so this red one oscillates through, the blue one, the magnetic field goes. And what happens when they hit the receiver antenna? Well, you have an electric field, a changing electric field near a conductor, right? electric fields act on charges. So they're going to make the charges in here do whatever they are trying to make it do. And so they will zap, 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 as you can picture as the electric field makes its way through. Zoop, zoop. Just kind of take this, right? And so redrawing it here, you can kind of see, remember, an electric field is a vector. So when we're drawing the waves like this, right, we're saying, okay, it peaks upwards in this direction, and then it kind of peaks downwards, right? That direction peaks upwards. That's what these waves are. It's changing magnitudes and directions of the electric field, oscillating from this max to this max in the other direction. So the field is the direction it's going to cause charges to go, right? Defined as what it would make a positive charge do, but it can still make a negative charge do something, right? And so as the electric field comes in, you can imagine what's it making charges do there, okay? So the antenna is not the one moving, the wave is moving, right? But just imagine the wave is coming into the antenna like this, right? And so it goes, right? It forces them up, 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 and then down, 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 and then up, 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 and then down, and it goes on and on forever like that, right? As it comes through, it's going to make them, the charges in there oscillate between up, down, up, down, up, down. It's going to cause that oscillation of the charges in the receiving antenna. Which leads us into kind of an idea here now of a more of a practical, everyday term type thing. Okay, transmitters and receivers. So transmitters transmit, they send it out, right? Essentially a transmitter sends, okay, and receivers, do I need to say what they do? They receive, right? So radios, Wi-Fi, cell phone signals, all of it works on this transmission / reception principle predicted by Maxwell and then here demonstrated by Hertz. So in other words, if you can create some electromagnetic waves, send them out, transmit them, and something's out there to receive them, well, it will receive them with the same frequency that you sent it out. So in other words, you can transmit some message as long as you encode it with the right frequency and someone else can pick it up. Now, electromagnetic waves, they can travel far, right? In fact, look up at a star, right? That's electromagnetic waves traveling to you from literally billions of kilometers away. Okay, so they can go pretty far and still be pretty bright. Same goes for the signals here on Earth, right? This actually led to the first communication across an ocean in 1901. Okay, sometimes the years on this really make me stop and think and go, wow, in the 1900s, think of what was happening in the 1900s, right? Think of what was happening in the 1900s. You imagine the 1900s and you just think, wow, those guys didn't know anything, right? We knew this. We knew how to produce these things that we can't see and then how to encode information in them and then transmit them across the ocean. It's pretty impressive, right? For 120 years ago that they were doing this stuff. Okay? So again, transmission, reception, how's it work? Okay, changing current in some transmitting wire, right, creates an electromagnetic wave, which is again just a self-propagating series of perpendicular electric and magnetic fields. The wave travels to a receiving wire, that's your antenna, and upon arriving, it induces a current in it. And guess what? If you induce a current, you can do some useful stuff with that, especially when the current follows what the signal is saying. Now it says here, antennas must be parallel to the transmitter to work best. Let's think about why. So if we have our transmitter and we have our antenna, antenna is just a conducting wire, right? Transmitter is essentially the same thing. How does it work? Well, we have a charge, an electron, okay, essentially oscillating up and down. We're going to make it go zoop, 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 zoop. And since it's accelerating, it's going to produce a changing electric field, which leads to changing magnetic, which blah, 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 leads to an electromagnetic wave. Okay, I'll just draw the electric part because that's what's going to end up inducing the current, right? Now it says antennas must be parallel to the transmitter to work best. Okay, so imagine you're an electron in that receiving antenna. You're just sitting there, okay, and this has been oscillating, so it has been producing some electromagnetic wave. Again, I'm just drawing the electric part there because that's what's going to end up inducing the current, right? Now imagine you're in that antenna. Okay, whoops. Now imagine you're in that antenna and this field starts coming at you. Whoa, okay, I'm getting pushed up. Whoa, now I'm getting pushed down. Oh, up, oh, down, whoa, 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 right? So if you're that electron and this thing comes at you because it's been produced from this guy, right? So it's being produced here and now this electromagnetic wave is coming at you, right? You can see that's going to make you go up, down, up, down. So that is going to, whoops, so that is, you betcha, right? That is going to cause you to oscillate. Now, what if, though, it says must be parallel to work best, okay? What if you had one completely perpendicular? What if you did not take their advice and you tried to make an antenna work that was perpendicular to the electromagnetic field that works? So we have our antenna parallel. Let's do an antenna perpendicular. Okay, now again, imagine you're an electron in there and you have a changing electric field, well, changing electromagnetic field, but again, kind of the electric part that's important here, right? Coming at you. Now, you feel that push, but can you move in your, but are you really going to move in your antenna, right? Not really. You get pushed up, you get pushed down, but you can't move in that axis, right? Your axis to move in is flat here. So it's really not going to do much for you. Remember, these are waves, right? So if you pick a point on each thing, think back to physics 20 when we were doing a mechanical wave, right? If you're in the water, you bob up and down and up and down and up and down, but you don't really get pushed side to side. Same thing here. There's no axis of motion that electron's free to move in. So that's why it works best when it's parallel and worse when it's perpendicular. Okay, so there we go. Now it also says antennas work best if they are about half a wavelength long. Okay, let's break that down a little bit here. So I'm going to make my incoming electromagnetic field, but just focusing on the electric part for now. Okay, I'm going to take my antenna. What's a wavelength here? Remember, a full wavelength is crest to crest or trough to trough or whatever, as long as they're doing the exact same thing at each point, right? So those are all wavelengths. Lambda, lambda, lambda. Okay. Now it says they work best if they're about half a wavelength long. Now, why would that be? Well, think about the amplitude that you go through in half of a wavelength. In half of a wavelength, you go from the max change in electric field being this way to the other way, right? So in half of a wavelength, you go from max to min, essentially, right? From peak to trough, from crest to trough. And so what that means is you're going to get the most kind of bang for your buck when that electric field travels through, right? Right? You're going to kind of get the most bang for your buck. If it's about half a wavelength, then as that half wavelength passes through, right, you're kind of getting the most efficient use out of your wire. It's going to cause the maximum oscillations possible because you go from, in a half a wavelength, you go from a max to a min, right? Min to max, min to max. So in that half wavelength antenna, you're getting max to min in your oscillations. Okay, so just to summarize here, antenna, if it's perpendicular, right, electrons not moved by changing electric field. Okay, whereas here, electrons get max motion from changing electric field. Again, in half of a wavelength, right? And so in one half of a wavelength, basically the change in electric field is maximum. Okay, so again, in our everyday sense, yes, antennas are wires that you receive some electromagnetic signal, but realistically, an antenna is just something that receives electromagnetic transmissions, right? So for example, how does a microwave oven work? Well, it works because water molecules are polar. You might know that from your chemistry class, right? All that means is they have a slightly negatively charged side and a slightly positively charged side. In other words, overall, yes, their charge is zero, but when you look at a water molecule, it is kind of a charge, right? It's got kind of two charges going on there. Overall, it's neutral to a chemist, yeah, but to a physicist, when we look at that, we say, hey, there's some charge hanging out here, okay? And so as the electromagnetic waves, which again are made of changing electric and magnetic fields, pass through the food, they do what these guys are doing to the electrons. They cause those water molecules to vibrate, okay, causing the food to warm up. So in this case, the food is the antenna, with the motion of the water molecules in it being the induced motion of charge, right? So that is why you might have heard that microwaves only work on things with water, right? Truth is, they'll work on metal too, because metal's a conductor, and don't put metal in your microwave, you'll get charge motion and it won't look good. Okay, right? So think back to your earlier science classes, particle model of matter. What is heat? What is temperature? It's just particles moving quickly, right? So if you can make water molecules vibrate by putting a changing electric field over them, electromagnetic field, right? Well, then you're going to make that object warm up. So if I turn the microwave on, okay, notice that we have our changing. It's just showing the electric field part here because that's what's going to end up being interesting. But since these are charged, right, they are affected by a changing electric field, and you see the more they move, the more motion you get, and then you see the temperature go up here as well. So food is the antenna. Water molecules are the charges inside the food that are going to get affected by the changing electric field. Okay. Now, your eyes can act as antennas. Specifically, your retina can act as an antenna, right? Why do you see stuff? Well, you see visible light because the electromagnetic waves vibrate electrons, right? So visible light waves come in, they hit the back of our eye, they hit our retina, and they induce a current in our retina. They really do, right? They're moving electrons. Hey, that's charge, that's moving charge, that's a current, okay? Which transmit an electric signal along neurons to our brain. So why, when you look at your hand, are you seeing your hand? Well, electromagnetic waves in the visible light wavelength are bouncing off of your hand, hitting the back of your retina, and that changing electric field is causing electrons in your retina to send an electric signal to your brain's sight center that says, hey, I'm seeing a hand right now, right? It's a little mind-blowing to think about, okay? Really cool, okay? So in that case, the retina is the antenna, okay, with electrons moving through your neurons being the induced current. So again, just hammering home the point of what's an antenna. An antenna is just simply something that receives an electromagnetic signal and has a current induced in it because of that electromagnetic wave that's coming to it, right? And that current is used for something, okay? So just a quick kind of, I know we've been talking about it, but let's really just kind of quickly go through this review, okay? Physics 20 review, wave parameters. So words we use to describe waves, basically, okay? Now, light and all other forms of EMR have the exact same ones from the ones we studied in Physics 20, okay? So it's important to have these down. They're going to be important as we go. So wavelength is the distance between two different consecutive points on either the B or E field where the field is changing in the same way, okay? That's a fancy long way of saying, right, crest to crest or trough to trough. Now, you don't have to go crest to crest or trough to trough. Those are the easiest ones to A, see, and B, not mess up. Okay, what I mean by that is some people go, oh, I'll go middle to middle. Okay, you can go middle to middle, but you need to go the same point. You need to make sure it's doing the exact same thing. So what I mean by that is, okay, if we want to look at a wavelength, remember the symbol for that is lambda, the Greek letter lambda, okay? So if we're looking at wavelength, wavelength is just the distance between 2 points where the wave is doing the exact same thing. That's how I think of it, okay? So crest to crest, definitely that's a wavelength, okay? Trough to trough, definitely that's a wavelength. And the mistake students make, so don't do this, okay, is they go, oh, middle to middle, that's a wavelength, right? How can these all be the same length, right? That's not. Look at that one. It's about half a wavelength if you're looking at it, right? Why is that not a full wavelength? Because here, look, it's going up. It's at the middle and it's going up. Here, it's at the middle and it's going down. So it hasn't done a full oscillation yet, right? That's a wavelength, is the distance it takes to do one full oscillation. So we now need to go, okay, to when it's doing the exact same thing. Aha, there we go. Now it's gone from going up back to the middle, but going down. There we go. Now it's in the middle and it's going up. So that is a full wavelength. Okay, all those are full wavelengths. All right, amplitude is the maximum magnitude that the magnetic or electric field reach as they oscillate. Okay, so it's essentially half of the total change that they go. Half of the total change, meaning total change being crest to trough or trough to crest. Amplitude is just the height from the middle to a crest or the middle to a trough, right? That's the amplitude. And it's the magnitude of the B or the E field. So it's a little more complicated because this is an electromagnetic field, but really, essentially, it's not that far off of the electric field. When is it the biggest in newtons per coulomb? When is the magnetic field the biggest in Tesla? Okay, there is a little more complex math to combine the fields, but it's not much conceptually beyond what we've been talking about. Where is the E field the biggest? Where is the B field the biggest? So again, if we draw our wave, and then I'm going to put in a kind of a midpoint, right? So the point where the E field or the B field would be 0. What's the amplitude? Well, it's this height, right? That is the amplitude, okay? Or this could be the amplitude. But it's not the whole thing. Be careful. Students want to say this is the amplitude. No, that's not. That's 2 amplitudes. What does amplitude mean for a wave? Well, it's essentially going to mean its intensity. What does amplitude mean for an electromagnetic wave? Well, it's essentially going to mean its brightness, you can think of it as for now, right? If you're thinking of a light wave, the bigger the amplitude, the brighter the wave is. So it's not going to change the color. It's not going to change anything like that. It's just going to be more of the same color, right? So if you have So to go back to, remember, in sound, we said if we change the amplitude, do we hear a higher frequency or a lower frequency? No, you just hear the same sound louder, right? The same pitch, but louder. So imagine if I had green light, what would green light with a bigger amplitude but the same wavelength look like? It would look like a bright green light. Okay, the same way I can go in that frequency, and I can go in basically the same frequency, just a bit louder. Okay, frequency though, that is where things change in terms of what the light actually will look like, or the EMR will look like. So frequency is the number of oscillations the B or E fields, the B and E fields together, complete per second. So frequency, just like it always has been, is cycles per second. So the number of times they go from crest back to crest or from trough back to trough every second. That's what you can think about it, okay? So how many times do they go from crest to crest or trough to trough? So to show you what I mean, here's a low frequency light, maybe like red light, okay? Red light would do this, right? Maybe 1 second has gone by. Well, red light would go faster than that, but you get the point, right? If 1 second has gone by and this whole time, right, it has went from, okay, crest, trough, crest, okay, there's one cycle, trough, crest, okay, it made 2 full cycles, almost, 2 in a little bit, right? What would high frequency look like? Okay, so in this one, 1 second went by. What would high frequency look like? Well, it's just going to do more. In the same amount of time, it's going to do more full cycles. So there, that's high frequency. Okay. Again, how long did this take? If this took the same amount of time, it took 1 second, then look how many cycles it made, right? Trough, trough, that's 1. Trough, 2. Trough, 3. Trough, 4. Back to trough, 5. Almost back to trough, 6. So this has 6 times this has 6 full cycles in 1 second. So we would say this has a frequency of 6 hertz. We would say this has a frequency of, what did we say? Was it 2? Yeah, about 2 hertz. 2 cycles per second. Okay, so let's maybe even write that in. This has a frequency of about 6 hertz. By the way, these are nowhere near the actual frequencies you would see from electromagnetic ones, but we're just kind of going through the definitions again, right? Okay, this one did about 1, 2, about 2 hertz. Okay, so again, frequency, just how many crest to crests and how many trough to troughs. How many full cycles can you do in 1 second? Okay, now wave or propagation speed is how fast the wave actually moves through space. Okay, now this has always been true, but so if you think of an ocean wave, right, or so if you think of a pond and you drop a rock in, you can watch the wave in the water propagate out, right? Now, for electromagnetic radiation, it still has a speed, okay? In a vacuum, which means in empty space, right, for all forms of electromagnetic radiation, all of them, radio, microwave, gamma, whatever, all of them, it is always C, we call it. Perhaps the most important constant in physics, okay? You know what, I'll say it. It is the most important constant in physics. I'll make that commitment, okay? The speed of light in a vacuum, okay? This is always the same. This is actually the universal speed limit. Nothing can go faster than that. Do we really know that yet? Not yet, per se, but it would be coming soon in the world of physics, and it would have some pretty wonky side effects that would change everything we ever understood to be true, but that's neither here nor there, okay? Now, often we just call c the speed of light, okay? And I will do that a lot too, because let's be honest, that's what we usually call it, right? It's true, light's a form of EMR. Just remember that all EMR, all electromagnetic radiation propagates at c. It's not just visible light. Lastly, one of the big things we needed from physics, one of the big things we did with waves in physics 20 was the use of the universal wave equation, okay? That universal means universal, it works for every wave. And so that is that the speed of the wave is equal to the frequency times the wavelength. If that seems weird to you, remember, frequency equals 1 over the period. What is period? Well, frequency is number of cycles in a second, right? Period is just number of seconds in one cycle, right? So it's how long does it take for it to go from one crest to the next crest, right? So essentially, V equals lambda, the wavelength, over t, period. So in other words, how far did you go? Crest to crest divided by how long it took you to go from crest to crest. Hey, this is just V equals d over t, right? It's just V equals d over t. Now, here's the thing. Whenever we're dealing with EMR, V is just C. So you can use the universal wave equation. It's just that V is C is 3.0 times 10 to the 8 meters per second. So if you're ever given the frequency of light and asked to find its wavelength, and you go, well, they didn't tell me the speed. If it's EMR, you betcha they did. It's on the back of your formula sheet. You got to know that all EMR in a vacuum travels at 300,000 kilometers per second. Okay. So again, the speed of light is just that. It's just a speed. So it still works with V equals D over T. So if I ask you, we've talked a lot about electromagnetic radiation. What's the math like with it? So radio stations, you know those numbers on radio stations? Guess what that talks about? It actually talks about the frequency of their electromagnetic radiation, the frequency of the radio waves they put out. So Mix 103.7 has a carrier frequency of 103.7 megahertz. Be careful, megahertz. So 100 mega means, right? Mega means 10 to the 6, right? A million. So what is actually oscillating at this frequency? So if the frequency that's coming out is 103.7, right, megahertz, it's saying, well, what's actually doing what's creating it essentially, right? Why are these electromagnetic waves being producing? Well, electrons in a transmitter somewhere down at the radio station. Okay, so what's happening in some transmitter down at the radio station? We have electrons vibrating up and down at a frequency of 103.7 times 10 to the 6 hertz. Okay, so how is it created? Well, besides what we just said, right? We make the electrons oscillate. How do we do that? Well, essentially, it's the same setup Hertz had, right? So you have something with alternating current, right? You have something with alternating current, switch it back and forth so that you can make electrons go back and forth, right? All you got to do is change the voltages so that it wants to go one way and then it wants to go the other way and then it wants to go one way and wants to go the other way. You just need an alternator, okay? So transmitter creates alternating current. Really, it just changes electron direction over and over and over and over again. Up, down, up, down, up, down, whatever it might be, right? So we got a change in current leads to a change in electric field, right? As Maxwell taught us, right? We normally would have said change in current, hey, change in magnetic field. That's what we would have said last unit, right? But that leads to a change in magnetic field. That leads to a change in electric field. That leads to a change in magnetic field, on and on and on and on until us at home sitting with our radio turned on. Now our antenna picks up that electromagnetic wave. It induces a current in our antenna. Now we can listen. Okay, so that's this change in current eventually. So this is our antenna receiver. This is a change in current down at the transmitter. All right, what's the wavelength of this EMR? Well, what do we have? Let's write down our givens. We've got that the frequency equals 103.7 megahertz, so times 10 to the 6 hertz. Okay. It's asking for the wavelength. So we've got an F, we've got a lambda. Missing anything? Now be careful, right? Seems like we're missing something if we're going to use this guy, except this is a radio wave. So it's a type of electromagnetic radiation. So V equals C equals 3.0 times 10 to the 8 meters per second, 300,000 kilometers per second. So what's the wavelength? Well, new equation. Let's manipulate it. So divided by the frequency, and lambda, the wavelength, is equal to V over F, which is equal to 3.0 times 10 to the 8th power meters per second, divided by a frequency of 103.7 times 10 to the 6 megahertz, and two significant digits, because yes, we have to use 2 because this is a rounded value, right? So 3, whoops, it's actually 3 sig digs because it's given on your data sheet as 3.00. So 3.00 times 10 to the 8. Okay. I got that the wavelength of this would be 2.89 meters. There we go. That sounds right. That's about radio, right? As long as it's, so really anything above a couple centimeters, that's going to be radio. So this is nice. This is a good way to check your work. You do kind of have to know the electromagnetic spectrum, okay? You do kind of need to know the rough, very rough. You definitely need to know the order, okay? But you roughly should be able to say, okay, yes, that should be radio. I'm not going to test you too hard. You do definitely need to know which ones are visible. Again, you'll get there with practice, okay? But yeah. All right, if you live 10 kilometers away from the station, how long does it take the signal to get to you? So, how fast is it going? And how far does it have to go? We know how fast it's going, right? V is c. We know how far it has to go. It has to go 10 kilometers, so d equals 10 kilometers, right? V equals 3.00 times 10 to the 8th meter per second, right? Yeah, it's moving fast, but it's still just moving. So V equals d over t. Nice thing, light will never accelerate. Okay, you will never have to do accelerated motion with light. Light cannot accelerate. If it can, at least in the way you understand acceleration, we have to throw out the last 100 years of physics. So hopefully it can't. Okay, V equals d over t, and we want t, so multiply by t, and then divide by v. I'm just going to do those both in one step if you don't mind. So t equals d over v equals 10,000 meters over 300,000 kilometers per second, or 3.0 times 10 to the 8 meters per second. And I got that to get to your house 10 kilometers away, the time it would take would be 3.33 times 10 to the negative 5 seconds, right? 10 kilometers away, right? Light's fast. I mean, it's the fastest thing there is. It actually turns out to be kind of slow when we look at the size of the universe, but for us on Earth here in our everyday light, yeah, very fast. Okay, what's the optimal antenna length? So remember, we're trying to get most bang for our buck with that electric field coming in, right? And so we would like the antenna to be, since an electromagnetic field goes from max to min, right? Goes from max to min in 1/2 of a wavelength. Well, that's how big our antenna should be. So the optimal antenna length would be 1/2 lambda, which is 1/2 of 2.89 meters, giving you 1.45 meters. Okay, a definition that is going to come up again later, but let's look at it now, okay, just because it kind of makes sense to introduce the idea now. Polarized just means oscillating or restricted to one direction, right? So in one dimension, you can oscillate or vibrate, okay? So are electrons oscillating in an antenna and or receiver polarized? What do you think? Well, if I'm an electron in an antenna, can I move in any dimension other than this one? Up, down? No, right? So yeah, they are polarized, which actually ends up meaning that the light they produce is also going to be polarized. The EMR they produce is going to be polarized, okay? So I've been kind of lying to you when I've been showing EMR this so far. It's been this nice up-down electric field and this nice side-to-side magnetic field. True that every single electric field will have a perpendicular magnetic field. Realistically, we think of light that way. It's simpler to draw it and everything, but what does light, really unpolarized light, looks like? It has electric fields kind of in all 360 degrees, and then magnetic fields perpendicular to those electromagnetic fields, but perpendicular through all the 360 degrees, right? So that's more of a realistic picture, except everywhere, of what unpolarized light would look like. However, since the electrons are only oscillating up and down, the electric field is only changing in that direction, right? If we have charge motion in all directions, that's kind of what we'll get here. But in this case, yes, this is definitely going to be polarized light, which actually explains, you might not remember this, but I do, bunny ears on the TV, right? You actually kind of had to move them. You wouldn't receive a picture if you didn't have them moved to the right place, right? You had to move it around to kind of get different channels. Okay, now a mystery wave. Electrons vibrate with a frequency of 1.2 times 10 to the 11 hertz. What type of wave is being picked up by this antenna? So we're picking up some signal with that frequency, and we're saying, hey, what are we picking up here? So frequency 1.2 times 10 to the 11 hertz. Okay, well, that's actually enough information right there to think about it. I don't know about you, but for me, it's honestly always easier to think in wavelength. I don't know why, it's just kind of my brain, the way my brain works with it. So if you are one who is going to go and try and memorize roughly the frequency ranges, by all means, go ahead. For me, I can remember really easily that visible light is between 350 and 700 nanometers. And once I've got that, I can kind of ballpark some stuff. So I'm just going to go ahead and find the wavelength. Technically, this is enough. I'm going to find the wavelength. So wavelength would be V over F. Remember, a hertz is in inverse second, so the units will work out here. I have seconds to the -1 over seconds to the -1. Okay, so for me, for whatever reason, that's easier for me to think about because now I know, okay, this is way bigger than visible light because visible light would be times 10 to the -9, and this thing is only times 10 to the -3. Okay, and then just in terms of ballparking, right? You know, visible light is right smack dab in the middle of the electromagnetic spectrum, which means there's three with longer wavelengths, right? Radio, microwave, and infrared. And then there's three with smaller wavelengths, the ultraviolet, X-ray, and gamma. Okay, so this is obviously bigger. This is a bigger wavelength than light. So we are either radio, micro, or infrared, right? Now remember, if you can remember that visible light, the biggest wavelength it can have is 750 nanometers, right? Look at this. This is nowhere near that. This is way bigger. So infrared would be pretty close to that, right? So this can't be infrared. Then if you can remember that radio, really radio deals with something on the order of meters, right? Once you hit meters, you're kind of talking about radio. And then that puts this right smack dab in the middle, right? So I happen to know that microwave is around the centimeter range, right? But you can also just kind of construct it from saying too small to be radio, too big to be infrared. This is probably microwave, and you'd be right because the range for microwaves is about 10 to the -1 meters greater than lambda greater than 10 to the -4 meters. Okay. By all means, you could have also done this. You could have done the frequency way and said, well, right off the bat, without even finding the wavelength, microwave, because 10 to the 9 is lower than the frequency, lower than 10 to the 12, right? And that falls right in the microwave range. For me, whatever it is, I don't know. I find it easier to think about in wavelengths. By all means, if you like frequencies better, go ahead. Okay, sketching graphs again, just a reminder. Okay, we've gone through this before. These are kind of the questions you should ask yourself every time, right? Where should it begin? Does it increase or decrease? Does our responding increase or decrease as we increase or decrease our manipulated, right? Does it follow a linear or a curved relationship? If it's curved, how quickly does it curve? Okay, and finally, are the intercepts possible? Students vary the frequency of an alternating current and measure the speed of the resulting electromagnetic wave. Sketch the graph showing the expected result. So first things first, what goes on the Y, what goes on the X? Well, as always, responding goes on the Y, manipulated goes on the X. So what do we manipulate here? We varied the frequency, right? Varied the frequency. So manipulated, that's going to go on the X. Okay, of an alternating current and measure the speed. We measured the speed. Okay, measure the speed. We measure our responding variable. So that goes on the Y. Okay, so we have the speed as a function of frequency for an electromagnetic wave. How is speed going to be affected by frequency? Well, what are we talking about here? We're talking about the speed of an electromagnetic wave, right? Does speed ever change? No, it is always, 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 always. It's a constant. 3 times 10 to the 8 meters per second. Okay, does not change. Again, though, this actually isn't that weird. It's not like I'm saying, boom, light doesn't change, deal with it, right? You can actually think about this. If you change the frequency with which you are making waves in the water, do you change how quickly the waves move? No, you kind of just change how big they are, right? If you go slower, those waves are still going to go at the same speed outward, assuming you're not changing the medium that they're traveling through, right? So the speed of light is a constant. Changing frequency will actually just lead the wavelength to go down so that they end up not changing, so that the speed ends up staying the same. Okay, now students repeat the experiment, but this time they measure the effect of frequency on wavelength. So the effect of frequency, that means manipulated on wavelength, right? So what is the effect on our responding? Okay, so we're going to do wavelength as a function of frequency. Now, let's look at the equation. We've got, I'm going to say C equals F lambda. So that really drives home the point that C does not change, right? So if C does not change, let's just solve this. How does lambda depend on the frequency? How does the wavelength depend on the frequency? Okay, so as frequency gets bigger, as I put a bigger number in the denominator, as I divide by a bigger number, what's going to happen to the wavelength? Well, bigger frequency, smaller wavelength, right? And that checks out with, just kind of take a second and picture EMR, right? If I go shorter wavelength, right, I get a faster frequency, okay? So sure enough, it's an inverse equation. So lambda, the wavelength, is proportional to 1 over the frequency. What does that look like? Be careful, it doesn't look like that, because then it's saying you could have zero, your intercepts don't make sense, right? How could you have zero wavelength but still have some frequency? That doesn't make sense, right? If you have no wavelength, you don't have a finite frequency. And same for the other intercept, right? If you have zero frequency, how could you have some finite wavelength, right? So this is an inverse relationship purely for a mathematical reason. Frequency is zero, this thing breaks down, it goes to infinity, right? And vice versa if you'd solved it the other way. So that is what an inverse relationship sort of looks like. I didn't do a great job of drawing that, but it's essentially the idea, okay? Now, straightening graphs, that's not going away either. So what is the trick to straightening graphs? Well, I think of it as, don't think about plotting the data. Forget about the data. Forget about the F and the lambda, whatever. Ask yourself, how do I plot a straight graph based on the equation, right? Think purely in terms of the equation to get a straight line, to get a straight graph. So what I mean by that is straighten the wavelength frequency graph. Well, whoops, V equals F lambda. Again, why do we want a straight graph? Well, any kind of graphical analysis requires a straight line, right, to do slope or area or intercept on. So V equals F lambda, okay? We are trying to plot wavelength as a function of frequency. So wavelength equals V over F, like we said before. Now, again, we said wavelength is proportional to 1 over frequency. So wavelength is inversely proportional to the frequency. I agree. Wavelength is inversely proportional to the frequency. But wavelength, as we've just said, and you would have no problem agreeing with if you agree that it's inversely proportional to frequency, we just said wavelength is directly linearly proportional to 1 over the frequency. So hey, it's our graph. We can plot what we want. Let's graph wavelength as a function of 1 over the frequency. Now, to actually sketch it, it's proportional, it's linearly proportional, but let's really quickly think about the intercept. Can we have a wavelength of 0? So realistically, can we have 0 here? Can we have a wavelength of 0 and a frequency of 1 over 0? Not really. So we can't really go through the origin, but technically, I guess we can go just a little bit to the right of it. We could have a huge frequency so that this is very small, and then also a very small wavelength. So I wouldn't put it through the origin, but you can put it just a little bit to the right of that.
And why might we have made a straight graph like this? Well, remember, we straighten graphs so we can get some slope or intercept or area, right? Let's think about it. What would be the slope of this guy? Well, right, slope would be y over x, rise over run. So lambda over 1 over f. Well, that's the same as, right, dividing by a fraction is the same as multiplying by the reciprocal. So, and hey, f times the wavelength. What is that? That would be, if this is an electromagnetic wave, speed of light, right?
If you're looking for practice of this, specific questions that are related directly to this will be in the Google Classroom or the agenda.